Welcome to the next lecture on heat treatment. This week we are trying to cover crystal structure. Then the third lecture is on heat treatment. Heat treatment is a very important process because when you try to process, for example, when you try to machine a workpiece, or when you try to deform a workpiece, or when you try to join a workpiece, the material property plays a very important role. So, in the last lecture towards the end we saw iron carbide diagram. In the iron carbide diagram, you could see how does the microstructural changes happen with respect to temperature and composition. Heat treatment is one wherein which it can change the properties, mechanical properties. Sometimes it can also change the hardness on the surface. It can do all through a treatment or it can do only on the surface. So, heat treatment is a very important process wherein which you can change the behavior of the material. Sometimes you might be given a situation where I cannot change the shape or the size of the material or of the part, but I wanted to improve their mechanical properties. Then heat treatment is the only option. I have a shaft or a pen, the surface of the pen is getting worn out. I have to do some surface treatment such that I can prevent the wearing. Then surface treatment is part of heat treatment. So, in the content we will see the introduction, then purpose, then classification, stages of heating, soaking and cooling, different types of heat treatment processes, benefits and their recap. Heat treatment itself can run to 42 lectures. If you try to take material science course, one full unit will be heat treatment. Here in which we are trying to give you a superficial understanding such that you can appreciate the heat treatment process. Heat treatment is an important operation in manufacturing process of many machine parts and tools which impart higher mechanical properties to steel. So, you take a workpiece like a shaft. This shaft is now getting heat treated. By doing the heat treatment, you can try to play only on the surface. Only on the surface you can try to do a heat treatment, or you can try to do the bulk. All to all you can do. The full properties can be changed. You can try to bring austenized surface layer. So, austenization, you can go back and refer to your iron carbide diagram. Stress relieving is also part of heat treatment. You are trying to deform a material. When you try to deform a material, a shaft is there. When you are trying to deform the shaft, you are trying to bend it. So, here there will be tensile stress, here there will be compressive stress. Now, in the shaft itself, you have two different stresses getting introduced. I wanted to relieve these stresses. Then what do? I do stress relieving. Stress relieving is a heat treatment process aimed at improving the properties of strain hardened metals. It involves heating the metal to a moderate temperature, which relieves the internal stresses, reduces hardness and increase ductility. Achieving a tough core through the process of case hardening is also possible, wherein which only the surface you hardened, not through to through. So, what is the purpose of heat treatment? It enhances the mechanical characteristics of a material such that its hardness, tensile strength, shock resistance, ductility and corrosion resistance improve. So, if you want to enhance any of these properties, you can try to play with heat treatment. Improving machinability while minimizing the brittleness, elevating internal stresses in metals caused by hot and cold working process. It also helps in modifying or refining the grain structure. You want to make smaller grain structure, by heat treatment you can do. Augmenting the magnetic and the electric properties, increasing both the corrosion resistance and wear resistance are possible by heat treatment. It also enhances the surface hardness of material, boosting the fatigue limits of medium and small components including gears, wrist pins and shafts. When you see heat treatment, it is classified into two. You can do throughout the material, that is called as bulk. If you want to do only surface, on top of a surface, you can try to do only on the surface, I can try to do. Only selectively in this portion I want to do, that is also possible. I am talking, this is from the side view, this is from the plan view. Only the center portion of the shaft you want to do it, you can do that. So, bulk and surface are two categories of heat treatment. When we try to talk about bulk, we have annealing, normalizing, hardening and tempering. We also have Marr tempering and austenitic tempering. Annealing, normalizing, hardening and tempering. These are the classifications under bulk. And again in annealing, you have full annealing, recrystallizing annealing and stress relief annealing. When we go towards the surface, you have two properties. One is thermal, the other one is thermochemical. Thermal means you can do flame, induction or laser. When we try to talk about thermochemical, it is carburizing, nitriding and carbonitriding, a mixture of these two. So, here surface, flame hardening. So, when we try to introduce a flame heating on the surface, you can try to do bending or you can try to relieve stresses. You can try to play with this. So, this is the major classification of heat treatment. Now, annealing, normalizing, hardening, you cannot change the shape and size of the material. So, all you can do is play with the temperature and time, that is all. So, putting this inside a furnace, now I try to play with the temperature, time and see what is the response or achieve what do I want. So, here it is going to be temperature versus time plot. So, I heat it to a certain temperature, then I quickly cool it, I slowly cool it, right, or I heat it and then I instantly quench it into water or something. So, all these things are now going to be used for bulk heat treatment. The fundamental is this: heat treatment has multiple stages. So, let us understand these stages. Heat treatment generally consists of three primary stages: slow heating of the metal to ensure the maintenance of the uniform temperature by the metal. If I do not do a slow heating, if I do a sudden heating, then what will happen is the core will be very soft or it will not have anything. The surface will try to take the hard values. Okay. Slow heating of the metal, it ensures the maintenance of uniform temperature by the material. The soaking or holding of metal at a specific temperature for a stipulated period is soaking or holding. So, what I am trying to say is, I will slowly heat it. This is temperature, this is time. I slowly will heat, then I maintain at a certain temperature, then I slowly cool. So, these are the stages. So, the first stage is going to be heating, the next stage is going to be cooling and this is going to be soaking. Okay. So, heating and cooling are there. You can have heating, you can have again two things. You can have fast, you can have slow. Same way you can have cooling, you can have fast and you can have slow. Each of it has its own response. You can have a fast heating and a slow cooling possible. So, if I put fast, slow, heating and cooling, you can have fast heating and cooling, then slow is possible, then you can have a combination of these two depending upon your requirements. And you know very clearly, since you have gone through the iron carbide diagram, the temperature has a clear response of the microstructure getting formed. The microstructure in turn has a direct response on the mechanical properties. So, you can have a slow heating, so that the entire material is heated. You can do soaking or holding. Soaking or holding is this. So, wherein which the temperature at a specified temperature it is there, so that the transformation in the microstructure can happen, and then you have a metal cooling under room temperature conditions. Heating stage. During the heating stage, the main objective is to achieve a consistent temperature distribution throughout the material. If there is improper distribution of temperature, then you can have thermal induced stresses. So, this thermal induced stresses allows you to warp the material. The shaft whatever is there, it can warp like this, because there is not much of distribution of temperature, so that the metal can cool. It ensures uniform heating. It is essential to increase the thermal gradient. If the heating is uneven, different areas of the metal may expand to varying rates, which will try to either distort or it can try to crack. When the gradient is very steep, there can be cracks, there can be distortions. So, generally the uniform heating, it is essential to increase the temperature gradually. In the soaking stage, this phase entails maintaining the metal at a specific temperature until the internal structure is achieved. So, you wanted martensite, you wanted austenite, you wanted pearlite, you wanted leduberite getting mixed in this. So, here what you do is you try to soak and keep it for some time, such that the internal structure is all transformed to get what is required. The soaking duration refers to the time the metal is kept at a constant temperature. In case of irregular cross sections, the soaking time is generally determined by the largest cross section. For example, you have something like a funnel. So, this area dictates the soaking time. Cooling stage. The cooling technique employed can differ depending on the specific type of metal and may utilize cooling medium such as liquid, gas or a combination. For example, we many a times what we do is we try to take a bath. Inside a bath, we fill it up with liquid. This can be water, oil. So, we quench the material. When we quench the material, it can be a sudden cooling. If you have an oil, the cooling rate will be much lower. So, you can also blow air and then cool it. So, you can think of liquid, you can think of gas, or you can think of something like a steam also, depending upon your application. The rate at which the cooling occurs is affected by both the metal itself and the selected media. So, liquid media, solid media, or a gas media, you can choose. Solid media is, you can also try to have some salts and then you can quench it in that salt. So, then there is a diffusion of the salt also happens on the surface. If you see a blacksmith, he always tries to put coal fully covering the hot rod, and then he tries to heat it and then he tries to hammer it. So, when the coal is around, it tries to burn the iron, and there is a possibility of carbon getting diffused into the surface, and when it gets diffused, it forms cementite, or the carbon surface is hardened, and once he gets the shape, immediately he quenches to retain the shape. A blacksmith does it. That is how they have been doing a sword, that is how they have been doing lot of utensils and other things at home. Right. So, the rate at which the cooling occurs is affected by both the metal itself and the selected media, making this process vital for obtaining desired properties of metals. Now, let us see annealing. So, now we saw these are the stages of heat treatment. Now, we are trying to take under bulk each of these processes: annealing, normalizing, hardening and tempering. Annealing. Annealing is a heat treatment process that involves heating an alloy above its phase transformation temperature. Phase transformation temperature, where there is a change of phases, right, above its phase transformation temperature, followed by slow cooling. The process significantly alters the mechanical property such as strength and ductility of any given material is changed drastically. So, what we do? We try to take a shaft. This shaft is heated to a phase transformation temperature and then allow to slow cool. Slow cool is, they put it inside a furnace and allow the furnace to slowly reduce the temperature and get cold. Additionally, it has refinement of grain structure, which can improve the overall performance. Annealing is the heating of steel and cooling slowly in the furnace. So, annealing is heating and furnace cooling is annealing. The purpose of annealing is to reduce the hardness, to improve machinability, to restore ductility, to relieve all the internal stresses and to eliminate structural inhomogeneity. So, for doing all these things, we always anneal the given sample. So, in annealing, there can be 4 types of annealing. One is called as diffusion annealing. Then we have spheroidal annealing, which full annealing and process annealing. So, if you see, full annealing is A1 to A3. Where is this A1, A3 coming? If you go back to your iron carbide diagram, I would have mentioned A1, A3, right. So, you do a heating, then soaking, then cooling. Partial annealing means you do not go below A3 and then you do a slow cooling. Subcritical cooling is you do not even cross A1 temperature and then you soak it for a longer time and then cool it. So, diffusion annealing, also known as homogenization within alloy steel, ingots and casting. The process involves heating the material to a high temperature, typically 1000 to 1200, and allow it to do a furnace cooling. What is diffusion annealing? After reaching the desired temperature, then cooled slowly within the furnace to 800 to 850 degrees Celsius before being air cooled. So, here what do? Is we try to take it to a temperature, and then what we do is, after that we hold it for some time, then we do slow cooling, right. Slow cooling we do. So, it follows like this, and once it reaches a temperature, certain critical temperature, then what we do is we do a quick air cooling. So, following homogenization, full annealing is typically performed to refine the microstructures of casting. Higher temperature gradually accelerates the diffusion process. So, we saw diffusion annealing. So, in diffusion annealing, we try to take it to a temperature of 800 to 850 and then do air cooling. So, if you see this diagram, it is pretty interesting. So, you initially heat, then you soak it for some time. So, then you try to slowly heat, then you try to soak, then you heat, then you soak, and then you allow them to have an air cooling. Then air cooling means you take it from the furnace, put it outside in the free atmosphere, or you force an air, or you try to do a slow cooling, keep it inside an oven, so the temperature slowly decreases in the oven. So, the heating interruption to avoid formation of any cracks, because moment you keep on be increasing, there is a thermal shock. This thermal shock tries to break or crack. So, what we do is heat it, soak it, heat it, soak it, heat it, soak it. Okay, they do it step by step such that you get it. Full annealing. Full annealing, heating the steel above its critical temperature. Hypoeutectoid steels are heated above the upper critical temperature, while the hypoeutectoid steels are heated above the lower critical temperature. So, this is the lower critical range, and then this is the higher critical range. This is a higher critical range, right. So, you see full annealing happening here. So, lower critical range. Holding the steel at this temperature for a sufficient time, typically 3 to 4 minutes per millimeter of thickness for a thick section. You hold it for this. So, 3 to 4 minutes if I say, then you will not, even for a flat surface can we do that. So, it is 3 to 4 minutes per millimeter. This is very important, right. So, that you can try to calculate the thickness and then you will see what is the sufficient time of holding. So, again A1, A3 are there. So, here you can see spheroidizing, process annealing and stress relieving. Spheroidized annealing. Spheroidized annealing is designed for high carbon steels which are notoriously difficult to machine, but due to its hardness. So, spheroidized annealing is hard to machine because of its hardness. This process transforms the carbide structure within the steel into small spherical globules. So, the grains are there. So, globules will be formed. These globules while machining is hard. To achieve this, the steel is heated to a temperature just below the lower critical temperature, held at a temperature for a period and then slowly cooled to 600 degrees Celsius at a rate of 25 to 30 degrees Celsius per hour. So, this is spheroidal. So, you try to take it to 730 to 770 and then you try to bring it down 25 degrees to 30 degrees per hour, you slowly cool it. Process annealing. If you go back, there are 4 annealing process: diffusion annealing, spheroidal annealing, full annealing and process annealing. So, if you look at it, process annealing, the temperature happens here. Process annealing is primarily used at low carbon steel, right. By heating the steel below the lower critical temperature A1, deformed grain recrystallizing, leading to increase in ductility and stress relieving is process annealing. Below this temperature, we try to do that. The annealing temperature varies depending upon the factors like degree of cold working, initial grain size and holding time. So, the process annealing temperature changes. Next is normalizing. Normalizing is a final heat treatment process for components experiencing stress relieving. So, this is normalizing, you can see here. So, strain and nominal stress. So, when we try to do a normalized sample, you get the response. When you see an annealed sample, you get a response like this. Normalized sample, you see a huge strain we get. Okay. So, normalizing is the final heat treatment process for components experiencing significant stresses. It involves heating steel slightly above the austenitic stability temperature, holding it briefly and then air cooling it. Holding it briefly, in annealing it was furnace cooling. Here in normalizing it will be air cooling. So, you see the ductility, the strain whatever you get is very high. This results in a microstructure of ferrite and pearlite in hypoeutectoid steels and pearlite and cementite in hypereutectoid steels. Now, it is very clear how the microstructure is formed. Ferrite and pearlite are formed in hypereutectoid. All these things you should please refer to your iron carbide diagram. Normalizing enhances yield strength, ultimate tensile strength and impact strength. Normalized steel are harder and stronger than the annealed steel of the same composition, but exhibits lower ductility. In annealing, what happens is you do a furnace cooling. Here you do air cooling. So, if you try to look at normalization process and annealing process, so temperature versus time, you see a coarser grain. The material is heated 30 to 50 degrees above the upper critical temperature. Now, you see what happens to the microstructure. The temperature is held until the grain structure becomes uniform. From here, there is, suppose if there is a carbon here, all these things will get diffused inside the grain and then you get it. So, on air cooling it, material is air cooled back to room temperature, you see fine grain structures are getting formed. Okay. So, you see at temperatures and then while cooling what happens. So, this is material is air cooled to get this structure. So, coarse grains are converted into fine grains during the process of normalization. Again, this we are talking at with respect to steel, iron, but if you try to do copper and other things, you might have different microstructures. When we try to do annealing, we have high strength microstructure. So, when you do a soft annealing, you see here deformation and easily machinable microstructures are formed. High strength anneal, you get this in structure. Hardening and tempering, this is the next one. The process is conducted in 3 steps. First, the object is heated to a temperature higher than the critical point. Then, it is held at the elevated period for a elevated temperature for a specific period. Finally, the object is rapidly cooled by immersing it in a quenching media like water, salt bath and oil. You can also have air cooling. Air matlab something like nitriding. So, something like that. You can have a nitrogen passing through it. So, you can also have water, salt or oil and gases also. So, hardening is a process which is very important. Here it is held at a certain temperature for a certain period of time and then rapidly cooled. Quenching. Quenching is a process of rapid cooling of metals using various substances as we have discussed earlier. Brine solution, air, water, oil, etc., etc. While quenching is often linked to the hardening of the metal. It does not always lead to hardening. It can also try to reduce the hardening. Compared to water quenching, oil offers several advantages. Because water, when you quench it in water, what happens is the heat gets transferred to water, the water starts bubbling and then it forms a jacket around it. So, once it forms a jacket around it, the performance is different. So, oil quenching is always preferred. It provided range, minimizing the risk of quenching defects like distortion and cracking. In oil, it is reduced. The cooling capacity of oil remains relatively stable over a wide range. The oil bath are widely used for quenching alloy steel due to their controlled cooling characteristic. Tempering, hardening and tempering. Tempering involves heating the hardened steel to a temperature below the lower critical temperature, hold it for a specific period of time and then cool it slowly. Tempering is heating the hardened steel to a temperature below the lower critical temperature. This is very important. Martensite formed during quenching exhibits extremely brittleness and often contains higher level of residual stresses. To improve the property, a subsequent heat treatment process called as tempering is always done. Martensite is the hardest, right? Hardest microstructure. So, it when you do quenching, formed during quenching, exhibits extreme brittleness and contains very high residual stress and it is very hard. This is a final step in heat treatment process. You do tempering and then you try to remove the brittleness and try to induce ductility. High temperature tempering, medium temperature tempering, low temperature tempering, these are the different types of tempering process. This process typically performs tempering around about 500 to 650 degrees Celsius. Medium temperature tempering is typically conducted with a range of 350 to 500 degrees Celsius. So, 500 to 650 is high, 350 to 500 is medium and anything less than 250, typically 250 degrees Celsius and less for 1 to 3 hours. The process is commonly used in the manufacturing of measuring tools and cutting tools. We do low temperature tempering. So that what we do is we get a sustained stable microstructure. So the heat treatment benefits are it relieving residual stress, it enhances ductility, it increases toughness. The tempering temperature significantly influences the final property. Higher tempering temperature leads to lower residual stress, reducing hardness and increased toughness. After tempering, the steel typically cooled slowly to minimize the development of new thermal stresses. Case hardening. So, these are till now whatever we studied was part of annealing, normalizing, hardening and tempering. We saw that. Now, what we are going to do is surface treatment. So, that is case hardening. Let us see case hardening. Case hardening, the hardened outer layer is referred as a case, while the softer, more ductile inner is called as a core. The case hardening is a process that creates a hard, wear resistant surface on a soft core material. This technique is particularly useful for components subjected to wear and impact, as it combines the benefit of a durable surface with the toughness of the underlying core. The case hardness typically follows the order nitriding, then cyaniding, then carburizing. This case hardening is exhaustively used in automobile industry, toy industry, domestic industry, many places they use. Carburizing. So, carburizing. Carburizing is a process used to harden the surface of low carbon steel. During carburizing, the steel is heated in a carbon rich environment at around about 870 degrees Celsius. Carburizing is nothing but what I told you, a blacksmith. This process infuses carbon into the surface layer, increases its carbon content to approximately 1%. After carburizing, the workpiece undergoes a hardening treatment followed by low temperature tempering to achieve the desired combination of toughness and hardness. So, after you do case hardening, carburizing, you do a low temperature tempering also. 3Fe plus 2CO leads to Fe3C plus CO2. Fe3C is austenite with dissolved carbon at 870 degrees Celsius, the maximum amount of carbon it can be dissolved in austenite. The carburizing is performed by varying ways. It can be packed, it can be gas, it can be liquid. So, you have a bath, the liquid can dissociate and then bring you carbon. The gas what you infuse can bring in carbon. The pack whatever you have, a coal, that can also induce carbon. The part are immersed in a carburizing mixture and then sealed within a steel box using clay to prevent any gas exchange, that is pack carburizing. Gas carburizing, the work is treated in a medium of gas containing CO and hydrocarbon gas such as methane, propane, butane, etc. to give gas carburizing. Liquid carburizing, this process uses a molten bath containing 20% of sodium cyanide which serves as a source of both carbon and nitrogen. The process heat treatment is done up to 950 degrees Celsius and then you do carburizing. So, if you see here, gears are carburized. Any moving part, wheel axle parts are carburized. Night riding. Night riding is a surface hardening process wherein the nitrogen content of the steel surface is increased. So, what we are talking about is on the surface, this on top and bottom, carburizing and night riding here. Okay. This is achieved by heating the steel component in an atmosphere of ammonia, NH3, within a airtight container at temperature ranging from 500 degrees to 650 degrees. Every process you should try to remember the temperature, and this temperature you will get in mind when you try to memorize or keep in mind the iron carbide diagram. The ammonium gas is continuously circulated through a container wherein which 2NH3 is dissociated into 2N and 3H2. The atomic nitrogen diffusion into steel surface reacts with the alloying element like ammonium, chromium and molybdenum to form very hard nitrides. Aluminium nitride, chromium nitride, molybdenum nitride can be formed, and this is giving you a very hard surface. The steel containing approximately 3% of these alloying steels typically produce hardest case. So, the typical nitriding case depth can be 0.3 to 5 millimeter, which usually requires 30 to 40 hours, where the temperature has to be maintained from 500 to 520 degrees Celsius. So, if you see temperature, time is very important, right? In heat treatment, temperature and time is very important. So, to reduce the processing time, a two-stage process can be 30-40 hours. To reduce it, a two-stage process can be employed, where the workpiece is initially heated to 500 to 520 degrees and then it follows a second stage of 550 to 600 degrees Celsius for nitriding. Cyaniding, the workpiece are immersed in a molten sand bath containing 20 to 30% of sodium cyanide, 25 to 50% of NaCl, 25 to 50% of sodium carbonate, and heated to a temperature between 800 degrees Celsius, 820 degrees Celsius to 860 degrees Celsius. This process introduces carbon and nitrogen into the steel surface. After a holding time of 30 to 90 minutes, the workpiece is immediately quenched in water, so that you get this cyaniding on top of a surface. The subsequent low temperature tempering at 200 degrees Celsius is typically performed to increase the mechanical property like ductility. To recap, in this lecture, what we went through was what is heat treatment process and purpose, different stages of heat treatment, what are the different heat treatment process like annealing, tempering, normalizing and carburizing. We also saw the benefits. So, now let us do a small exercise as an assignment for our understanding and appreciating of heat treatment. So, let us try to take a candle, wax, you heat it, it goes to a liquid. Now, you pour the entire liquid in oil, water and free air. See what is happening during the process, what shape and size it is forming, right. So, you try to do this for a wax. Then let us try to do one more exercise. In this exercise, what you do is you try to take what is material available in the household. I am just trying to see. So, you can try to take oil, okay, heat the oil and try to quench a air heated spoon. So, that means to say you take a steel spoon, you heat it in the flame till it becomes little red hot, then you try to oil quench it, you try to quench it with water, then you try to quench it with forced air. That means to say you have a fan and then you hold it. Now, you see the temperature versus time plot you do, see what is the response you get. So, that means to say the red hotness has to come down to normal. So, when you do this, after doing it, you have to see the shape and size of the wax, what did you pour. Here you will try to bend the spoon. The spoon whatever is there, you will try to bend the spoon. After doing all these things, oil heating, bring it to room temperature and then bend it. Water quenching, bring it to room temperature, do it. Forced air cooling, bring it to room temperature and then bend. Make sure you do not hurt yourself. These two will clearly demonstrate what is the influence of heat treatment with respect to the output. These are the reference books which we have used for making the slides, and thank you very much.